In the last segment, we studied percentiles, what they were and how to find them. And what we did was we approximated them from histograms, assuming that the individuals were uniformly distributed within bars. And we said that that assumption isn't necessarily always sensible. So it's a good idea to know how to find percentiles directly if you have the entire list of numbers, just to be on the safe side. And so what we're going to do now is take a look at a little tiny example list and work out some percentiles. Now, if I want to find out how this list is distributed, step one, always, please, arrange in increasing order. And once you've got it in increasing order, then some things become rather easy. For example, what's the median? Well, it's 4 because the median is the halfway point, and here are 5 numbers, and there's a very clear halfway point. 4 has 2 numbers on one side and 2 on the other side. Very clearly, median equals 4. Little less clear when you have 6 numbers instead of 5. So I've taken the same list and I've just tacked on a 12 to the end of it. And now there are 2 middle numbers, 4 and 7. So what is the median now? Well, a natural answer is somewhere between 4 and 7. Halfway here? Why not? People often take that as a convention. Take the midpoint between the 2 middle numbers. And that happens to be 5.5 in this case. So is that a rule? Is that something somebody likes to do? Why not take 5.2? What's wrong with 5.2? If I took 5.2, it would be right over here. And it would be true that half the numbers are below it and half the numbers are above. So why not 5.2? Why not indeed? Mathematics isn't usually done by convention, though this convention is such a popular one that people have forgotten that there are other ways of looking at percentiles, and indeed there is something very precise that can be calculated. To illustrate why you need a more precise definition, let's just look at not the median, but the 25th percentile. If you want the 25th percentile of the list, you first need to know how far along the list you need to go, and how far along the list you need to go is 25% of 6 entries. So here are your 6 entries. You're going to go 25% of the way along. 25% of 6 happens to be 1.5, and the reason I have it in quotes is you can't have 1.5 entries. Entries are whole numbers. You either have them the first entry or the second entry or the third entry, but the 1.5th entry does not exist. So you're looking for a value that is there. So what value do you take? Do you want to take 1? Sure, you could take 1. How about 0.5? What if I wanted 0.5? Is that bad? What if somebody wanted 1.83? That's a bit weird, but is it wrong? These aren't matters of convention. It's a good idea to have one definition that works for all lists and all percentiles so that we don't have to worry about what's the convention in this case. And so what we're going to do is we're going to take the natural idea that the 25th percentile of this list has to be somewhere between 0 and 2 and try and work out where exactly it should lie. And for this, we are very much helped by a formal definition of the percentile, which I will read out to you, even though I know you can read perfectly well on your screen. I will read out to you because it's a bit of a mouthful. The pth percentile of a list of numbers is the smallest number that is at least as large as p% of the list. And I'm going to tell you, when you read that sentence, if your head is swimming a little bit, I don't blame you. It's that kind of sentence. Why don't we try translating that thing into English? So let's take our old familiar list and our old familiar 25th percentile that we were trying to find, and we already said it's got to be somewhere in between 0 and 2. Right? We didn't say exactly where, in between 0 and 2. So let us see what this definition says about the 25th percentile. What I'm going to do is I'm just going to look at the first number on the list. That's 0. That is the first out of 6 numbers, so it's a sixth of the way, that is 16.67% of the way into the list. And so it's definitely as large as 16.67% of the list. What is it as large as? Well, it's the smallest number on the list, so it's as large as itself. That's all it's as large as. And it's as large as 1 out of the 6 numbers. Which means that it is not at least as large as 25% of the numbers. So it is not a good candidate for the 25th percentile, and this is not surprising. So now we look at the next number on the list, and that is 2, and that is 1/3 of the way into the list, 2 out of 6 of the way. And so that is definitely at least as large as 25% of the list. 25% of the list would be somewhere here, this imaginary entry that does not exist. And that is the first number on this list that's in increasing order for which we can make this claim, that it is at least as large as 1/4 of the list. And so therefore, by our definition here, that is our candidate for the 25th percentile. And just to make sure that these other numbers aren't really getting into the act, let's take a look at number 4. This number is where on the list? It is exactly halfway through the list. 3 out of 6 of the entries. It's the 3rd out of 6 entries, 50% of the way into the list. So it is as large or more as 25% of the list, but it is not the smallest number about which you can say that. It got beaten by 2. We said that about 2 already, and so because the definition requires the smallest number, 2 wins. 25th percentile equals 2. And just to make sure that everybody understands why the smallest number matters here, it's because you're saying it's a number that is at least as large as P% of the list. So it's at least as large as 25% of the list. Well, look at number 12. That's at least as large as everything on the list. So it's at least as large as 25%, it's at least as large as 50%, and yet you don't want 12 to be every single percentile in the world. So what they're saying is try and get as close to 25% as you can, but from the top. So what I'd like to do now is I'd like to go over the mechanics of how to use the definition, and it goes without saying that you will put the list in increasing order, and then you will identify the place in the list that is P% of the way from the bottom of the list. So you will look at the lowest number and then the next lowest number and the next lowest number and find where you get to P%. And if you're lucky, that might be a place that is exactly on the list, in which case you take that number. And if not, what do you do then? If not, you take the next one up. So let's do an example. Yes, it's a familiar list, and we will now find the median, which is, as you know, the 50th percentile. So what does the definition say to do? Well, it says put the list in increasing order. We've done that. Identify the place that is P% of the way from the bottom of the list. Well, P%, 50% of the way from the bottom. 50% from the bottom is halfway through, that's right here. 50% of 6 is equal to 3. And that is exactly on the list, that is 4, and that means the median is 4 by definition. Should we try another one? Why not? Before we do that, comparing this to the 5.5 that we had in our last calculation, that is halfway in between 4 and 7, it's different. It's formal. The nice thing about it is that you can take it to the next example, which is find the 40th percentile. You do exactly the same thing. 0.4 of 6 is 2.4. So that's not the second entry, that's not the third entry. 2.4 is here. And so what do? Your rule says take the next one up, 4. The 40th percentile is also 4. And while we're about it, you should check that if you look at the 60th, the 70th, and the 80th percentiles, they're all 7. Shall we try the 80th? 80% of 6, 0.8 times 6, is 4.8. So that's in between here and here. And so the rule says take the next one up, and there you've got 7. And what you're seeing here is that the definition has taken into account the fact that a list may have ties. A tie is when two numbers are the same. And that percents of entries aren't necessarily whole numbers. And so you've got to account for that. And so just to summarize why you are using this definition and no other, it's clear, it's unambiguous, it works for every list and every percent, and it gives you a sensible answer. And for those of you who go on to somewhat more abstract mathematics, you will find that this particular way of defining percentiles actually has a great deal of power. But that is for another day and another time. For now, the formal definition of percentile for a list of numbers is what we've just gone through. And now what I'd like to do is I would like to go to your textbook. So here's exercise 3.10 of your text. That's exercise 10 of chapter 3. And what is it asking you to do? It is asking you to find percentiles. And what's it giving you? It's giving you a practice data set. So a data set, I believe there are 25 numbers in here. And this first list is all higgledy-piggledy, the way the data normally arrive. And then, very kindly, it has been sorted into increasing order for you. And now you are asked to find various percentiles, 21st percentile, 39th percentile, and we have a routine now, so we're going to apply it. There are 25 entries in this list. I want the 21st percentile. So what do I have to do? I need to find 21% of 25 first. That's 0.21 times 25, which is 5.5. And honestly, I don't even care about the 0.5. I just know that it's 5 and a bit. So what do? I go to my list and I find entry 1, 2, 3, 4, 5 from the bottom, 5 and a bit, which means it's in the middle here. I take the next one up, minus 32. That's what my rule tells me to do. Now I'm going to plug it in to your textbook. And are we ready for this? Are we ready to see what the textbook says? Yay, got it right. So I think you are more than capable of filling out the rest of this table, don't you think? I'm glad you agree. Have fun.